Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, chemistry students, senior 6, welcome back. I'm Alan, still with you in the chemistry lessons. So we are still on our topic of electrochemistry. As you can see on the slide, looking at unit 12, which is about electrochemical cells and their applications. You see the car battery and the dry cell. All those are examples of electrochemical cells. So our target is to look at how do they generate the potential. Today's lesson is about the standard electrode potential of a half cell. So, briefly, let's take a quick recap on what we looked at in the lesson 1. Take a close look what we looked at in the lesson 1. We basically looked at how to come up with a whole complete electrochemical cell, whereby we say the electrochemical cell is just two half cells connected together, and so these two half cells each has a certain potential. And we talked about the potentials in terms of being a more negative potential if it releases electrons first, and a more positive potential if it easily gains electrons. So when the two cells are connected together, then they create a potential difference, which is measured by the voltmeter, as you see it over here. And the salt bridge is basically there to complete the circuit by allowing the ions to flow in the opposite direction of electrons. Electrons are flowing this way, then in this case the sulfate ions will move from copper to the zinc to balance up the charges. And so in that way we get a potential difference. That is what we looked at in the previous lesson, and I ended by giving you the exercise, which we called exercise 1. I believe you've already attempted it, so right now let's quickly go through this exercise, what is expected of you, or what are the possible answers, then we can go directly to today's content. So, the corrections to this exercise. What was part A was show on the diagram the flow of electrons and the current. I believe you did, and if you attempted it, now it's time we correct our responses or our answers. So, electrons will be flowing from the zinc electrode, which is the anode, to the copper electrode. Since zinc has a more negative potential, we looked at the factors that affect the electrode potentials. So due to lower ionization energies of zinc relative to copper, it will lose electrons, and so copper will gain electrons. And the current always flows in the opposite direction of electrons. So this is the answer: the flow of electrons this way and the flow of the current that way. Second question was, describe the possible observations occurring at the bulb and in solutions for the copper sulfate and the zinc 2-sulfate. So what do you think, or what did you come up with as the observations? Hope we are together. So basically on the light, on the bulb, we expect it to light up. You would see the place, if you're in a dark room, it will be more lighter. We expect light on the bulb because of the potential difference and the current flowing in this cell. Then the color of solutions. For copper, the container having copper 2-sulfate, the color would turn to colorless. That is from blue solution to colorless, because copper will be depleted by this reaction, as you see. As electrons come from zinc, they are gained by the copper cations depositing copper salt on the copper electrode. So with time, there will be no more copper cations in solution. And the solution is blue because of the complex, the hexa-aqua copper 2 ion, the complex, which is responsible for this color. So when we don't have more of the copper cations, because they are being deposited as you see the salt, then we shall have a colorless solution. For zinc container, since it is colorless and we're having more zinc ion cations coming into the solution, there will be no observable change. So these are the expected observations per the setup. Then the last question was, suppose we substitute or we replace copper half cell, this half cell, with magnesium. What would be the flow of electrons, current, and the ions? Directly, of course, from your chemistry, you know magnesium easily loses electrons, or it is more reactive than zinc. So we expect the flow of electrons to be from the magnesium half cell, which would be right here, to zinc. In other words, our current direction will reverse. Electrons will move from the magnesium, which is here, to zinc, and the current in the opposite direction of the electrons. So this was for you to draw it and indicate that is still yours. Keep it up and draw it up. The emphasis here is to explain to you what is happening so as you go and correct your responses. So that is it, a quick review of the previous lesson. Now let's go to today's content, standard electrode potential of a half cell. We already know a half cell, what makes up a half cell, using the example of our zinc and copper, and how to come up with the potentials per each half cell. So now in this case, we are to determine that standard electrode potential. So in the remaining minutes within this lesson, we shall look at what makes up the standard hydrogen electrode potential and how to use the standard electrode potential to determine the standard electrode potentials for other half cells or other half electrodes. And in this case, our key terms are She, you know what is a She, that is the standard hydrogen electrode, reduction potentials, and the electrochemical series. These are the three terms that we shall be working with much of the time. So, lesson objectives. I have two lesson objectives which we are to achieve. One is to describe the composition and the action of the She. She is actually a recognized abbreviation for standard hydrogen electrode, She, according to IUPAC. IUPAC is the International Union of Pure and Applied Chemistry. So this is recognized every time you're free to say She or speak standard hydrogen electrode. Then we explain how the standard electrode potential of a half cell is measured relative to She. So these are our two objectives. And as you see, this E theta implies the standard electrode potential. So, measuring the standard electrode potential of a half cell. A point to note is when two cells are connected, they create a potential difference. So you can measure a potential difference, but it's very, very hard to measure the potential for an isolated half cell. What do I mean in here? If I illustrate the copper and zinc half cell, I want you to clap your hands. Clap your hands. Two hands come together and make the sound, right? I want you to clap the hand for one hand. Clap it and see. Do you hear any sound? No sound at all, but let's clap using 2 hands. So in this case, it applies in the same way like the potentials for this electrochemical cell. When you have 2 half cells, each with a certain potential, and you connect them, they create that potential difference. It's like our hands, left and right. Bring them together, you create the sound, and that is the clapping. But if you have the right hand alone, if at all you shake it, however much you shake it, the sound it will create will not be vibrant like when you're using the 2 hands. So it is very, very hard to measure the potential for an isolated electrode because it will always require another electrode. Remember, potentials, we are talking of potential in respect to, potential with, or relative to something else. So in that way, there is always a need for a standard electrode from which or for which the other half cells can be compared to. And when this group of chemists, as I said it, are UPACA, International Union for Pure and Applied Chemistry. This is a union that encompasses or that heads everything that involves chemistry. So they sat and came up to an agreement and say, let's make hydrogen our reference electrode and give it a 0 potential. This is a crucial word, arbitrarily. Arbitrarily. Something which we agree and assume and say, let this be. We've agreed to give it this value. It's not that it has a 0 potential. Hydrogen electrode has a certain potential, but this is an agreement according to this union. And the reason is simply to create a reference electrode from which other half cells can be compared to. Remember our clapping of hands, or remember the potential difference relative to. You must be having 2 cells to create a potential difference, which is measured. So with this, that is an agreement. So every time we are to talk of the potential of a half cell, we must compare it with the standard hydrogen electrode. So that is a point to note. You may ask, why did they select hydrogen? We shall look at it later on, but let's look at this definition. So after us having the standard reference electrode, then it comes to the standard electrode potential of a half cell. It is that potential difference created when you have that half cell connected to the standard hydrogen electrode. In other words, these are now 2 cells connected together. So the potential difference that will be generated will be for that half cell since hydrogen has a 0 potential. So indicating we can have negative potential and positive potential relative to hydrogen, which has a 0. And this takes us to look at why was hydrogen selected. Because it fulfilled the set requirements. Again, who are those that set the requirements? This union for chemistry, pure and applied chemistry. So one of the requirements was it should be easy to prepare, then reach the equilibrium first, and be stable. When we talk of being stable, we mean it should not change, its potential should not change with time. So hydrogen conformed to that requirement. Yes, as I said before, it was arbitrarily given a 0 potential, but indeed hydrogen does not have a 0 potential. It has a potential, but it's not specifically 0. But due to the agreement, by convention, it was given a 0. And so by that factor, it conformed to that requirement. The second requirement was it should be built of materials which can be easily obtained. Hydrogen is easily obtained from natural gas or the oils which are surrounding us. We are surrounded by the natural gas, so you can get hydrogen from there, so hydrogen is easily obtained. And in that way, those two made hydrogen to be a reference electrode and be given a potential from which the rest can be compared to. So this takes me to look at what makes up the standard hydrogen electrode. So something to notice is hydrogen is a gas. We know that. So you can't easily get the gas molecules like this air you see. This is air, we have the gas molecules in here. So you will not easily get the gas molecules to produce electrical energy. That needed something to adsorb all the gas molecules to adsorb onto it. When we talk of adsorbent material, this is an example in here. This is adhesive. When you wrap it somewhere, it sticks. So in this way, we need something which can, whereby the hydrogen molecules can come and get stuck for it to generate electric energy. So in that case, the She has platinum or sometimes nickel. It depends on which metal catalyst is being used. In this case, they used platinum. So this is the setup for the She. How does it work? We're talking of standard, indicating we must include the standard conditions. What are those standard conditions? Pressure should be 1 atmosphere. Since this is a gas, we quantify it in terms of pressure it exerts. Then the concentration of solution should be 1 molar. You see, this is hydrogen gas in hydrogen ions. 1 molar here, then the pressure here, 1 atmosphere. So the platinum is acting as an electrode for it to avail the surface area for the reaction to occur. Remember, we talked of adsorbent material, something whereby the gas molecules will come and get stuck and get adsorbed for them to lose electrons. So what happens is, with this setup, the hydrogen gas is let through in, and it gets adsorbed onto the platinum surface. So with that, it loses electrons. You see the equation here, forming hydrogen cations. And the hydrogen cations in solution, these 1M hydrogen ions, will pick up electrons, forming hydrogen gas again. Those are so far the two tendencies. Remember when we looked at the tendencies that happen when you have a half cell. You will have hydrogen losing electrons, which we call oxidation, and the hydrogen proton gaining electrons, which we call reduction. So we would expect a certain potential in here, whether the gaining or losing outweighs, where the gaining outweighs the losing or the losing outweighs the gaining, to give it a more negative or a more positive. But because this is a standard reference electrode, it has a 0 potential. Whichever reaction that occurs, it's assumed to be the same to give us a 0 potential. Question, why was platinum selected? It had also a few unique characteristics that made it outstanding than nickel or the rest. One, it has a higher surface area for which the equilibrium can happen. This is what we mean. Platinum, the surface area provided for reaction is higher compared to nickel. And it is less reactive, indicating we don't expect platinum to cations in solution because it hardly forms those ions. So it will not disrupt this equilibrium to be formed, meaning it will not gain electrons or lose electrons in the process. And it is a good adsorber of hydrogen. But the prominent are these two: increased surface area and its less reactivity. So this is now the makeup of the She. with its potential already known. So how is it used to determine the potentials for other half cells? We're looking at an example of copper electrode. So this is the setup. What happens, just connect your She with the other half cell you want to determine. Then the potential difference that will be read by the voltmeter becomes the potential for that half cell, since we know that the She has a 0 potential. So this value you see will be for that half cell. For this case, copper, it has 0.3377 volts. So that is how you quickly measure up. You just connect your She to another half cell you want to determine, then the potential difference makes up the standard electrode potential for that cell. A few points to note. In such a kind of a setup, we have the left-hand side, this is the right-hand side, and this is the left-hand side. According to the way you're seeing it directly, do not look at your hands or do not refer it to your hands, just the way you're looking at the setup. This is the right-hand side, this is the left, and this is the right. So what happens, oxidation will always happen on the left-hand side, then reduction on the right-hand side. That is by the agreement. And one other factor, She will always be on the left-hand side. So we expect it either to lose electrons or to gain electrons. So for this setup, for instance, this is the cell reaction. The She with its potential 0 and the copper gaining electrons, and so it has a positive potential. Us understanding how to measure the E theta, or the standard electrode potential, we can see a few variations that come along, and that is the sign of the E theta. So, something you need to notice is all standard electrode potentials are always written as reduction potentials. What do I mean? Get the cation or the nonmetal, for that case, gain electrons. Hydrogen is gaining electrons, copper is gaining electrons, zinc is gaining electrons. Reduction, gain of electrons. So you will always see electrode potentials written like this. So when they are written like this, then there is an implication that comes with the sign of the standard electrode potential. Look closely. Look at copper and zinc. Of course, hydrogen is unique. That is, it has a 0. Copper is a positive value. Zinc is a negative value. So what is the meaning of those positives and the negatives? Positive potential, negative potential. What exactly does that imply? And this is what it implies. When you have a positive value, that means the half cell has a more positive potential relative to She. Remember, potential, we connect it to something else, relative to something, with respect to something. So the half cell for copper is more positive, then for zinc is more negative. And the negative value simply implies that the reaction that is actually occurring is in the opposite direction. Let me show you something in here. Negative, losing the cell has more potential to lose electrons. So the She in here loses electrons and the copper gains. That's why copper has a positive. When you connect the She to zinc, zinc loses electrons to the She. But remember, according to the convention, according to the agreement, the She should be on the left-hand side, should be just here, indicating we expect a She also to be losing electrons, but instead the She is gaining electrons from zinc. That's why the negative is here. So the voltmeter, for it to read you the exact 0.76, because zinc is losing electrons to the She, instead of She losing electrons to zinc. So that is what this negative implies, simple. It means this half cell is losing electrons to the She. And the positive, it implies this half cell is gaining electrons from the She. You see the illustration is clear there. So as we conclude, these are the standard electrode potentials for different cations. You can see from potassium to lead, they are negative, then copper is positive, going, and the iron and so on. So what you need to notice is the more reactive metals, they have a negative potential because they easily lose electrons compared to less reactive like copper and silver and so on. And so nonmetals, the more reactive nonmetals have a more positive potential. Look at fluorine, chlorine, and so on. So that is it with the potentials and how you can determine the potential difference. As usual, I can't leave without giving you an exercise. That is exercise 2. It's just to apply the knowledge we've gone through, which half cell is undergoing oxidation, and so on and so forth. So get some time, complete it. Thank you, Senior 6 Chemistry students, for being part of this. The next lesson will be very interesting, I promise you. Don't miss, endeavor to attend, please. Please stay safe. I want to see you in the next lesson. Bye.